An exponential function is a function in the form of f of x is equal to a to the x, where x is an exponent of some base a. We call a the base. And there are a couple of restrictions that we place on exponential functions. We say that the base a has to be a positive number. A must be greater than 0. And the reason for that is, let's say we had a base of minus 2, and our x was 1/2. This would be the same as the square root of minus 2, which is a non-real answer. It's a complex number. It's an imaginary number. And in between, and it's not only that we'd have to take a square root, but in between any two numbers, let's say between minus 1 and minus 2. Between minus 1 and minus 2, there are going to be an infinite amount of numbers that will not be in the domain, because you have to think. A square root won't be in there, a 4th root, a 6th root, an 8th root, a 10th root, a 12th root, and we can continue going on forever and ever. So in between 2 points, we would have an infinite number of holes in our graph that could not be part of the domain. So in order to avoid that and get a domain of all real numbers, what we do is we exclude negative numbers from the base. So we get a domain of negative infinity to positive infinity for exponential functions. And the reason we don't include we don't include a is equal to 1 is because if we have 1 raised to the second, it's the same as 1 times 1, which is equal to 1. If we have 1 raised to the third, it's equal to 1 times 1 times 1, which is equal to 1 as well. So the reason we don't include 1 is not necessarily because it's going to cause a problem in the domain or anything like that. We don't include it because it's useless, really. It's not going to give us any information. It's always going to be itself. So we don't include bases of 1 because we don't get anything useful out of it. So I think the best way to explain what exponential functions are is to compare it to a power function, which is something that we are used to seeing and dealing with. So I'm going to compare an exponential function to the power function x squared. I'm going to compare x squared to 2 to the x. And I'm going to start from 0, even though we're going to get some answers that are not necessarily that useful in the beginning. So we'll go from 0 to, let's say, 7. And the reason I'm including 0 and 1 is because when looking at exponential functions, it will be helpful to see what is going on when we have our 0 and 1. It will become more apparent of what is going on. So let's start filling in values, and let's talk about exactly what is happening when we put in a number for a power function and when we put in a number for a exponential function. So we'll go through the first two very quickly. We put in 0 here, we get 0. When we put in 0 for 2 to the x, however, we get 1. So if you forgot those properties of exponents, you should go back and review. If we put in 1 here, we're going to get 1. Put in 1 here, we get 2 to the first, which is 2. Here, we're going to get 4. It's 2 times 2. Here, we get 4 as well. We get 2 to the second which is the same as 2 times 2. Now we're going to start seeing the differences. Once we've gone on to 3, we're going to start seeing the differences between power functions and exponential functions. Here we know that 3 squared is 9. But what we've done when we've put in 3 for x squared, what we've essentially done is 3 squared, which is equal to 3 times 3. Now for 2 to the x, what we're doing is 2 to the third, which is 2 times 2 times 2. So 2 times. Here we did 2 times 2, we got 4. And then we're multiplying by 2 one more time. So we're going to get 8. 2 times 2 is 4, times 2 is 8. Now for 4, we're going to get 16. We know that well enough. 4 squared is equal to 4 times 4. For here, on our exponential, we're going to get 2 to the fourth, which is 2 times 2 times 2 times 2. And it's nearly identical to the preceding row, except that we're multiplying it by an additional 2. So we did 2 times 2 for the first one, which is 4, and then we did another 2 for 3, which is 8, and now we're going to multiply it by 2 again, so we're going to double it again. This is going to give us 16. So the same as x squared, but we got there by different means. For this power function we did 4 times 4, for here we did 2 times 2 times 2 times 2. But now we're going to start seeing separation between these two functions. Now we're going to get 25. 5 squared is equal to 5 times 5. Now here we're going to get 2 to the fifth. 2 times 2 times 2 times 2 times 2. So we're multiplying it by an additional 2 again from this previous one. And that's going to give us 32. And now what I'm going to do is just fill in the rest of this chart over here very quickly, because we know how power functions work. This 6 squared is equal to 6 times 6. And this one's going to be 49, which is equal to 7 squared, which is equal to 7 times 7. Now I really want to focus on this exponential function. What we should start seeing is a pattern emerging here. If we were to go to 6, it would be the exact same as 5, except multiplied by additional 2. So essentially we would double it again. And if we look at our chart, we can see a pattern of doubling. We started with 0, and we got 1. Then we did 1, and we got 2. We've doubled. Then we continued on, we went to 2, and we got 4. So we doubled again, 2 and 4. And then we doubled again. 2 times 4 is 8. Then we doubled again. 2 times 8 is 16, and we doubled again. So it's pretty reasonable to assume that we're going to double again. So let's say we do that. We get 64. 2 times 6, which is the same as 2 times 2 times 2 times 2 times 2 times 2. So we can see that this is exactly the same as the previous row, except we've multiplied it by one additional 2, so we can see where the doubling effect is taking place. All of these are the same as the previous row, except we've multiplied it by an additional 2. And this next row is going to be the same as this whole row. It's going to be the same as this whole row, except multiplied by an additional 2. So it's going to double again. And 2 to the 7th is in fact 128, which is double 64. So now we can see the difference between the exponential function and the power function. The power function over here, which happens to be a second power, is just squaring. It's just multiplying the number times itself. Here, it is multiplying the number by itself x amount of times. And we can see that it's increasing much, much faster than this power function. And in fact, an exponential function will be a power function eventually, no matter how high. It could be x to the 100th. Eventually, over time, this exponential function will become greater than it, because it keeps doubling and doubling and doubling and doubling and doubling and doubling. and this is only increasing by a set rate. Well, it's not really, well, the rate at which this is always going to be increasing. While a power function, its power is locked in place. As we recalled when we were talking about polynomials, how the greater polynomial, the greater power always wins in a graph in the long run. So an exponential function will always win. It's the function that can have the potential to increase the fastest out of all of them. So now that we've discussed this idea of doubling, let's look at one more example of let's look at one more example of an exponential function, because it's not as simple as doubling. It's not any exponential function is doubling. We should have a more, after this example we'll have a better idea of what an exponential function is. So this time I'm going to do 3 to the x. 0, 1, 2, 3, we'll do 7 again. 4, 5, 6, and 7. So 0 to anything is 1. Or 3 to, or anything to the 0 power is 1. 3 to the first is just 3. Now for 2, this is 3 to the second, which is 3 times 3, which is 9. Now 3 to the third, 3 to the third is equal to 3 times 3 times 3, which is 27. And to the fourth, 3 to the fourth, which is equal to 3 times 3 times 3 times 3. So it's going to be 27 multiplied by an additional 3, which is 81. Now for the fifth, this is going to be 3 to the fifth. This is going to be 3 multiplied by itself 5 times. So it's going to be the same, 3 times 3 times 3 times 3 times 3, multiplied by an additional 3. So it's going to be 81 times 3. This would be 243? 41? No, 43. Yeah, I did that right. 243. So now let's look at the pattern that's emerged from this. You can see we started with 1, then we've tripled to 3, then we've multiplied that by 3, so we triple again, we go to 9, then we triple again, then we go to 27, then we triple again, and we go to 81, then we triple again and go to 243. And then if we did 3 to, and then if we multiplied this by 3, that'd be 612, 729. And then if we tripled again, that'd be 2187. I think. Well, if it's wrong, just know that I tripled it. So what we've done is tripled. So what we can see now is a pattern of tripling. So now we can notice, now we can draw the conclusion that the rate at which this function is increasing is dependent on the base. In this example up here, we doubled every time we increased by 1x. In this example, we tripled every time we increased by 1x. So that's really what exponential functions are all about. We're going to be increasing by the rate of the base. So if we had a base of 4, so if we had 4 to the x, then we'd be quadrupling every time we went up by 1x. If we had 5 to the x, we'd be quintupling every time we went up by x. If we had 10 to the x, which is our scientific notation base. If you've ever taken a science class and you've learned about scientific notation, it's an exponential function essentially. Every time we increase x by 1, it increases by a factor of 10. So we have 10 to the first, which is equal to 10, 10 to the second, which is equal to 100, 10 to the third, which is equal to 1,000. And it does not only have to go positively, we can go negatively as well. Suppose we went, for these numbers over here, went -1, -2, -3, -4, -5, -6, and -7. These would be the same, except we would be taking the reciprocal. Because when we have a negative exponent, we take the reciprocal. So for -1, we get we get 1/3. So for -1, we get 1/3. For -2, we get 1/9. For -3, you'd get 1/27, and so on. So it works that way too. So now that we have a good understanding of what is happening in an exponential function, let's just evaluate a few exponential functions, just to get the idea of what we're going to be dealing with, or just a little bit of a hang of what's going to be going on. So let's say I have the function f of x is equal to 3x minus 2. And let's suppose I want to take the function value at 4. This works just like any polynomial that we've been dealing with. It's nothing different, except what we're doing is we're going to put 4 in the place of an exponent. We're going to have 4 minus 2, which is equal to 3 to the second, which is equal to 9. That's it. That was very simple. We'll do one more. We'll do f of x is equal to minus 2 times 10 to the x. And I want to know f of minus 2. Here it's alright that the base is being multiplied by a negative number. It's okay if the base is being multiplied by a negative number, as long as the base itself is not a negative number, because that'll create a problem in the domain. So what we can do is just substitute in minus 2. So we have minus 2 times 10, and then we substitute minus 2 in. And remember, when we have a negative exponent, we take the reciprocal of it. So 10 to the minus second is the same as 1/10 to the second, which is 1/100. So here we've got minus 2 times 1/100, which is equal to negative 2/100, which simplifies to negative 1/50.